Hello everyone, today we're diving into one of the most exciting topics in modern technology, quantum computing and in particular, qubits. You might have heard the buzz about qubits and wonder, what exactly are they? How do they differ from the bits in your computer and why are they so important? In this video, we'll break down what a qubit is, explore the various types of qubits, and look at some cutting-edge quantum processors from 2025. We'll also understand how quantum error correction works and touch on real-life applications that might change our world. So, let's get started. So, what is qubit? At its simplest, a qubit or a quantum bit is the basic unit of information in quantum computing. Much like the classical bit is the fundamental unit in traditional computing. But while a classical bit can only be either a 0 or a 1, a qubit can exist in a state of 0, 1, or a combination of both states at the same time, and this phenomenon is called superposition. Let's understand this with an example. Imagine a spinning coin. While it's in the air, it's not just heads or tails, it's in a state of both, until it lands and you measure the outcome. This superposition gives quantum computers the potential to process enormous amounts of data simultaneously. Now, another mind-bending property of qubits is entanglement. This is a truly strange phenomenon that only occurs in quantum mechanics. Entanglement means that when two or more qubits are entangled, their states become linked in such a way that the state of one qubit is dependent on the state of another, no matter how far apart they are. This happens even if the qubits are on opposite sides of the universe. Let's understand this with an example. Imagine you have two qubits, qubit A and qubit B. You put qubit A in a superposition of 0 and 1. Now, you entangle qubit A with qubit B. But here's the mind-blowing part. If you measure qubit A and find it in the state 0, qubit B will instantly know and will also be in the state 0 even if qubit B is on the other side of the planet. The same thing happens if you measure qubit A and find it in state 1, qubit B will instantly be in state 1 no matter how far apart they are. It's like having a magical pair of dice. If you roll one dice in New York and the other in Tokyo, the moment the first dice lands on a number, the second dice will automatically land on the same number instantly. It doesn't matter how far the dice are separated. That's entanglement. The key takeaway here is that when qubits are entangled, their states are tied together. This allows quantum computers to process complex data faster and solve problems that would be nearly impossible for classical computers. It's a concept that's still hard for us to wrap our heads around, but it's what makes quantum computing so powerful and different from anything we've seen before. Now, let's compare qubits with classical bits in a bit more detail. In a classical computer, every bit is like a tiny switch. It's either on, which means 1, or off, means 0. All the operations you do, from running apps to browsing the web, are handled by billions of these bits working in sequence. This binary system is very efficient for everyday tasks, but it hits limits when faced with complex problems, such as simulating the behavior of molecules or cracking large encryption codes. Qubits, on the other hand, operate in a quantum realm. Because of superposition, a single qubit can represent a multitude of possible outcomes simultaneously, and with entanglement, groups of qubits can work together in ways that multiply their computational power exponentially. This means that for certain problems, quantum computers can solve them much faster than classical computers, sometimes even exponentially faster. Now, there are several physical ways to create qubits, and today we're seeing breakthroughs in multiple technologies. Let's explore the main types of qubits and some recent processors which are in the news. First is the superconducting qubits. These are among the most common in today's quantum processors. They use tiny circuits made from superconducting materials, cooled to near absolute zero to eliminate electrical resistance. For example, Google's new quantum chip called Willow is a superconducting processor that features 105 qubits. Willow not only boasts increased qubit count compared to previous chips like Sycamore, but it also incorporates advanced error correction methods that reduce errors exponentially as more qubits are added. Second is trapped ion qubits. In these systems, individual ions, or charged atoms, are confined in electromagnetic traps and manipulated using lasers. Companies like IonQ and Quantinuum are pushing the boundaries with trapped ion systems. Trapped ion qubits are known for their long coherence times, meaning they can maintain their quantum state for longer, which is critical for complex computations. Then, third is photonic qubits. Photonic qubits use particles of light or photons to represent quantum information. They can be manipulated using optical fibers and beam splitters. While photons are excellent for quantum communication, Because they can travel long distances without significant loss, they're a bit more challenging to use for building scalable quantum processors. Companies like PSI Quantum are using photons or light particles to create qubits. These qubits operate at room temperature, which eliminates the need for extreme cooling. Fourth is topological qubits. A promising but still emerging technology, topological qubits rely on exotic particles called ions. These qubits are designed to be inherently resistant to errors thanks to their unique braid properties. Microsoft, for instance, is working on topological qubit architectures, such as a recent announcement of the Majorana 1 chip, that aim to achieve robust error correction naturally. Each of these types has its own advantages and challenges. Superconducting qubits, like those in Willow, are leading in sheer qubit count, while trapped ion qubits offer high fidelity. Also, photonic qubits excel in communication, and topological qubits promise intrinsic error resistance. Now, let's talk about a critical aspect of quantum computing is error correction. Qubits are incredibly sensitive. Even the tiniest interaction with the environment, like a stray photon or a tiny vibration, can cause errors in the quantum state, a phenomenon known as decoherence. This is why quantum computers are kept in ultra-cold and controlled environments. But one interesting thing is that you cannot simply copy a qubit to check for errors, like you might with classical bits, due to the no-cloning theorem in quantum mechanics. Instead, scientists use a process called quantum error correction. The idea is to encode one logical qubit into multiple physical qubits. For instance, techniques like the short code or the steam code spread the information of a single qubit across 7, 9, or even up to 1,000 physical qubits, depending on the system and the level of protection required. Recent breakthroughs in 2025 have focused on reducing the overhead needed for error correction. Google's Willow, for example, uses improved fabrication and innovative error suppression techniques to bring the error rate down as more qubits are added. This exponential error suppression means that by scaling up the number of qubits, the system becomes more reliable, a key milestone for achieving a fault-tolerant quantum computer. So, what can quantum computers do in the real world? Although they're still in the experimental stage, there are several exciting potential applications, like one is drug discovery and material science. Quantum computers can simulate molecular interactions at an atomic level, which is extremely challenging for classical computers. This could lead to the discovery of new drugs or materials with unique properties, like more efficient batteries or lightweight composites for aerospace. Second is optimization problems. Many industries, from logistics to finance, rely on solving complex optimization problems. Quantum computing could revolutionize how we schedule flights, route delivery trucks, or even manage supply chains, leading to significant cost savings and efficiency improvements. Third is cryptography and cybersecurity. One of the most talked about applications is in breaking and creating encryption methods. Quantum computers have the potential to crack many of the cryptographic systems currently used to secure data. That's why researchers are already developing quantum-resistant encryption protocols. Fourth is artificial intelligence and machine learning. Quantum algorithms can process and analyze vast amounts of data simultaneously, which may lead to advancements in AI. From training more efficient models to discovering patterns in big data, the synergy between AI and quantum computing could open new frontiers in research and technology. Fifth is weather forecasting and climate modeling. With the ability to simulate complex physical systems more efficiently, quantum computers could improve the accuracy of weather predictions and help us better understand climate change, aiding disaster preparedness and environmental protection. So that's it. Qubits are the fundamental building blocks of quantum computing, offering a revolutionary way to process information by taking advantage of superposition and entanglement. They differ from classical bits in that they can exist in multiple states simultaneously, opening up exponential computational power for specific problems. From superconducting qubits in Google's Willow chip to trapped ions, photonic, and topological qubits, researchers are exploring various technologies to build more stable and scalable quantum computers. Quantum error correction is a crucial part of this puzzle, ensuring that even the fragile qubits can work together reliably. While practical, everyday quantum computers may still be a few years away, the potential applications, from drug discovery to optimization, from improved cybersecurity to advanced AI, are both exciting and transformative. These breakthroughs are paving the way for the next major leap in technology, one that could eventually complement or even surpass classical computers in solving the world's most challenging problems. Thank you for watching. If you enjoyed this video, please give it a thumbs up and subscribe for more updates on the fascinating world of quantum computing. Also, hit the bell icon so you won't miss our future deep dives into cutting-edge technology. Until next time, keep questioning, keep exploring, and stay curious.